So the photoelectric effect is an experiment that supports the what type of theory? Particle, which is also called quantum. Yeah. Supports the particle theory, which is the same as saying quantum physics. When light shines on a metal surface, a photoelectric surface, electrons are emitted. So it's not just like a plastic surface or anything, it has to be that metal. And I'm not entirely sure, but my guess is because of a metallic bond has that kind of sea of electrons available. It's not so like tightly bound inside of a atom structure. So when light is shone on a metal surface, either electrons will be emitted immediately, there is no time for the electrons to build up energy and be ejected, or no electrons will be ejected at all. So kind of that threshold level. It's either it's an all or none, okay? All or none kind of principle. So here we have light coming in. Now this is a silly diagram because it shows it like a light bulb. So let's say this is UV light, but it doesn't really show that it's, because if it's just a plain light bulb it wouldn't work. So let's label that. UV light comes in. Here this plate represents a metal surface. So if UV light comes in, hits this metal surface, and electrons bounce off, so think about like the momentum comes in this way, it bounces off this way. So if electrons are traveling through this tube, this is like a vacuum. So it's traveling through this vacuum, it will travel this way. So now if there's a wire here, it will travel through the wire, and this is called a multimeter, and it will detect current. Okay, so then you can see if the electrons are flowing or not. Okay, they'll flow if it's UV light. If it's just visible light, you won't detect. Oh, I didn't do my minutes yet. That's what she's saying. So I'll show you another video that shows that.
So in this diagram, it is happening?
Yeah, because it shows electron flow, so it would have to be something like UV light or something greater than UV light, right? Something greater than UV light would make it happen too. So here's another lab demo showing kind of the differences and what I mean by the multimeter.
We're in the demo lab with Lonnie, where he set up a photoelectric effect experiment. He has white light impingent on a metal, and the energy of the photoelectrons emitted are shown on the meter at right. If he puts a red filter in the path, now only red photons can strike the metal, and you can see they do not have sufficient energy to eject photoelectrons. If we go to higher energy photons, say go to yellow light, that's shorter wavelength, and higher energy photons,
So just to note, I guess he is using visible light, but it's probably a metal that has a lower threshold than zinc was in that other example.
may be able to eject photoelectrons. And indeed, photoelectrons are emitted, but with a relatively small energy. If we go to higher still photon energy, green wavelengths, that's shorter wavelengths still, higher photon energies, we can see photoelectrons emitted at a higher energy. Now we can still go to higher energy photons. Blue photons, photons in the blue region, are the highest energy visible photons, and Lonnie has a blue filter that will pass only blue photons. Putting the blue filter in the path shows photoelectrons emitted at the highest energy. So here's an example of the photoelectric effect. Thanks, Lonnie, for that great demonstration.
Okay. So let's make note of that let's say the energy of EMR needed will depend on the type of metal. So I guess you can use visible light, so my apologies. You can use visible light, but it would have to be like a metal that has a lower threshold than, say, like zinc from that first example. Do you get it? Yeah? Okay. All right. So, to continue, this means that light/EMR is behaving like a particle. And that each photon either has the potential to collide with a single electron, so it's like one photon per one electron, and release the electron, or the photon doesn't have enough energy to release the electron. Again, an all or none principle. One photon only has the potential to release one electron from the metal surface. If no current was detected, this means that the photons had a frequency less than the threshold frequency. For that metal. Every metal has its own unique threshold frequency. The threshold frequency is the minimum frequency required to emit electrons from the metal surface.